Okay. Okay, hi everyone. I'm Edi Tribaskoro. Welcome again to our Combinatorics Today series. Good evening, good afternoon, and also good morning to all of you in various time zones. Today we will have a very special speaker, Professor Linda Lesniak, one of the world prominent combinatorists from the United States. She's from the Drew University, as well as from the Western Michigan University, USA. As we know that she's one of the authors of a famous book entitled Graf and Digraph, together with the Professor Gary Chartrand and Professor Ping Zhang. And now it comes, I think, in the 6th edition, and she's a well-known expert in the Hamiltonian graph. And also, I would like to welcome all colleagues, friends, and also students who are loyal in attending this program. We are very happy to have you, and thank you very much. So, hello, Professor Linda. How are you today?
Awake.
So, is everything fine there?
Wonderful.
Yeah, wonderful. Okay, so thank you for the accepting our invitation to talk in this series, and thank you for getting up earlier this morning to have a mathematics session in the early morning at 8 o'clock there, right?
Right.
Okay, so in this occasion, we would like to mention that this program is organized by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. And this year, we will have 14 editions, and today is going to be the 8th one. So we will have another 6 editions to go this year. And this program usually attended by students, academia, and researchers, not only from Indonesia, but also from various countries. And today, Professor Linda Lesniak will deliver a lecture with title The Necessary of Chvátal's Hamiltonian degree condition and forcibly p degree conditions, and will be chaired by Dr. Prita Etriana Putri. Before I give the control to Dr. Prita, we would like to have a photo together first. Yeah. So in that case, I like to invite Pak Adit, please have us to have a photo together, group photo.
Okay. Good evening, everyone. Good morning. Good afternoon.
Afternoon.
Yeah. Okay. So I would like to invite you to open up your camera so I can take your our pictures together. Maybe I will count from 10. So 10, 9, 8. Maybe it's too long, but yeah.
A very
5,
long smile.
4, 3, 2, 1. Once again, 3, 2, 1. Okay. Thank you, everyone.
Okay, thank you, Adit. And now I let Dr. Prita to chair this session. Okay, please, Dr. Prita.
Thank you, Pak Edi. Before we begin the session, I would like to introduce Professor Linda. Let me share a screen. Okay, good afternoon, good evening, and good morning, everyone. So today's Professor Linda will deliver a talk for Combinatorics today's series. And Professor Linda is a Professor Emeritus in Mathematics and Computer Science, Drew University. She also has affiliate faculty in Mathematics Department, Western Michigan University. She received her associate professor in Louisiana State University in 1974 until 1979, and then also in Western Michigan University in 1978 up to 1985. And she received her full professor in Drew University in 1985 up to 2008. She also has a lot of experience and also honors. I will mention just some of them. She is an editorial board, a Journal of Graph Theory from 1977 up to now. And then Graph Theory editor, Missouri Journal of Mathematical Science, 2008 until now. And also director of the IMEX Research and Education Institute, 1997 up to 2000, and also director of the IMEX Connect Institute, 2000 up to 2004. And she also director of Women in Graph Theory and Applications, WIGA, from 2018 up until now. Also, she is an organizer of Women in Combinatorics, 2018 until now. Like Professor Bhaskar mentions before, she wrote beautiful books that I believe all of the graph theorists already read about these books, Graphs and the Graphs with Chartrand. So this book has a 2 edition of English version and also, I'm sorry, a 6 edition, but one in English version and Japanese version. So that's quite nice. Okay, and so today she will give a talk about on the necessity of Chvátal's Hamiltonian degree condition and forcibly P degree conditions. I'm sorry if I wrong in pronunciation. So
I never can pronounce it quite right either.
Okay, Professor Linda's time is yours. Now you can begin your talk.
Okay, thank you.
You're welcome.
Well, I'd like to say hello before I start. I'd like to say, especially those of you who are here at 7 o'clock on a Friday night, you are to be commended. Well, it's hard for me to be awake, but you should be in the bars having a beer, you know, so it's very surprising that you're all here. I'm pleased. Okay. Oops, I don't think I have. Okay, I'm not sure what I do next. Do I share a screen?
Share screen, yes.
Yes.
Yeah, it's okay. I guess I have to do it again. All right, there we go. Okay, so I have a very long title here, and there's a lot of words in it. And if you don't know what all they mean, well, I'll tell you what they mean. But as she said, the title of my talk is on the necessity of Chvátal's theorem. Now, those of you who know what I'm talking about should be worried about this term right here, because really Chvátal gave a sufficient condition for Hamiltonian degree conditions. And I want to talk about why, in a certain sense, we believe it's almost necessary in a probabilistic sense. And we're going to talk about forcibly property degree conditions. So these are kind of the main ideas that are going to be in my talk. And I'm going to try to speak kind of slowly because where I come from, we talk really fast, and I'm always told that. So I'll try to keep it slower. So, okay. My clicker's not working to change the screen. I can't get the screen to move here. We got a problem. Let me see if my screen is locked. Nothing's happening. Oh, there we go. There we go. Okay. So the main idea that I'm going to be talking about are graphical sequence that force a property. So everything I talk about, when I say it's a graphical sequence of numbers, that means that there is at least one graph for which these are the degrees of the vertices. Okay, so that's underlying everything I talk about. So everything we will start with sequences that we know are graphical. And if that bothers you, don't let it, because there are many good algorithms for testing whether a sequence is graphical. So we're not losing anything by assuming that. We'll assume that the sequences are in non-decreasing order, always. And we're going to be talking about properties and sequences that force that property. That means that every graph that has that degree sequence has that property. That's what I mean by forcibly P. Because graphs can have the same degree sequence and be very different structurally. So we're going to be looking at sequences that have at least one graph with that sequence and force that graph to have some property. Okay. So the two properties that I'm going to be interested primarily today are that of being Hamiltonian, as Eddie said, this is an area I've worked in off and on throughout my career, which you've now found out is very long, which means I'm very old, but that's okay. And I'm going to be talking also about the property of being k-connected. So the P that we mostly will be talking about is that of being Hamiltonian and that of being connected. I'm going to look at sequences of numbers that force a graph to be either Hamiltonian or k-connected. Okay, so just in case you don't remember, a graph is Hamiltonian if you have a cycle in the graph. Now, by a cycle, I use that to mean you start at some vertex, you travel through the graph, you never repeat a vertex until you get to the last vertex. So that's what we mean by a cycle. And Hamiltonian means we have a cycle that contains every vertex of the graph. So we're going to be able to start at some vertex, go to every vertex in the graph, and then come back to where we started. So let's just look at some examples in case this is not a real familiar concept for you. These are two graphs that are complete bipartite. That means that there are two parts that have no edges in them. Like, let's look at this graph, K44. There are 4 vertices on the bottom. That's what I call a part. 4 vertices on the top, excuse me. And there are no edges in these parts. So that's what bipartite means. And the fact that it's complete, this K is from the German word for complete, means all the edges are in between. So we have K44, 4 vertices on the top, 4 on the bottom, all the edges in between. First of all, I want to claim that this graph is Hamiltonian. Well, since we don't have any theorems to use, we just have to crank out a Hamiltonian cycle, and it's fairly easy in this graph. I mean, I can start anywhere and just go up and down. Oops, 1, 2, 3, 4, 5, 6, 7, 8, and then back to where I started. So K44 is Hamiltonian. In fact, it has lots and lots of Hamiltonian cycles. And I think you can believe me that so would K55 be Hamiltonian, because I could just zigzag back and forth. And in fact, as long as I have the same number of vertices top and bottom, it's going to be Hamiltonian. So this graph is Hamiltonian. On the other hand, this complete bipartite graph with 3 vertices on the bottom and 4 on the top is not going to be Hamiltonian, because every cycle in a bipartite graph has to go back and forth from top to bottom. And if we don't have the same number of vertices on each side, we're going to get stuck up here. And then we haven't gotten everybody to get back to where we started. So here's an example of Hamiltonian. And in fact, any complete bipartite graph with the same number of vertices, and each part is going to be Hamiltonian. Here is a non-Hamiltonian graph. Anytime we have different number, top and bottom, it's going to be non-Hamiltonian. Kind of as an aside, the problem of determining if a graph is Hamiltonian is long been known to be NP complete. And if you don't know what that means, you should just think that nobody knows an efficient algorithm for, if I give you a graph saying yes or no, it's Hamiltonian. So no one has a good algorithm or a good characterization. That's the NP part. The complete part means if you ever found an algorithm that was efficient or a good characterization, well, first of all, you become very famous, but also this complete part means that you could translate that algorithm for determining if a graph is Hamiltonian to algorithms for lots of other problems that we don't know good algorithms for. So it would make you very famous. So a lot of work has been done in just determining sufficient conditions. Now, I don't mean, for the students here that have not written a lot of papers, to say that a condition is sufficient, that means that if the graph has that condition, then it's Hamiltonian. It's not an if and only if. There might be lots of Hamiltonian graphs that don't satisfy the condition, but at least it is sufficient to get some. So for example, here is the grandfather of all sufficient conditions for a graph to be Hamiltonian. This is a theorem of Dirac, and it's quite old. It's from 1952, and it's probably the first sufficient condition that was given for graphs to be Hamiltonian. And this condition said if you have a graph with n vertices, and every vertex has high enough degree, and the high enough is n/2, then the graph is Hamiltonian. Okay, it's not necessary and sufficient. That is, it's not if and only if. There are lots and lots of Hamiltonian graphs that do not satisfy this condition. But if you do, if a graph does, then it is Hamiltonian. Okay, so actually, let me go back to the previous screen. This graph, now, instead of having to build a Hamiltonian cycle, we can just use Dirac's theorem because we have 8 vertices and every vertex has degree 4. So it satisfies Dirac's theorem. So without having to look, we know it has a Hamiltonian cycle. Now, Dirac's theorem doesn't directly apply over here because it only tells you if it's a sufficient condition. So here we have degree 3 on some vertices and degree 4. They don't all have degree at least n/2. So it doesn't satisfy Dirac. So what? It doesn't tell us anything. However, it is an important graph because it shows us, you got to keep this in mind now, n is 7 here, and we have all the vertices have degree 3 or 4. So if you look at Dirac's theorem, it says n/2, but what that example showed is I can't lower this. I cannot say n-1/2, that if a graph had degree n-1/2, it'd be Hamiltonian, because we saw an example of a non-Hamiltonian graph there. So this theorem is, excuse me, best possible in the sense of minimum degree. Okay, if all you're going to do is a theorem about every vertex has degree at least something, this is the best you can say. And in terms of what I talked about in the previous slide about forcibly Hamiltonian, which is really what I want to aim at, Dirac's theorem would say this degree sequence, n/2, 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 is forcibly Hamiltonian. Any graph that has a sequence, or this particular sequence says it is graphical, and any graph that has that sequence is Hamiltonian. So that's really what I want to be looking at, a sequence that's forcibly Hamiltonian. It has to be graphical, and then you want to say every graph with that sequence is Hamiltonian. Okay, now what I said earlier was that there are a lot of graphs that are Hamiltonian that don't satisfy this particular condition. I mean, think of, and I'm sitting here waving my hands around and you can't even see me, but I'm sorry, that's how I talk. But if you thought about just a great big cycle. So take n vertices and just make them into a big cycle. Well, that graph is Hamiltonian, and every vertex has degree 2. So Dirac's theorem really misses a lot of Hamiltonian graphs because it doesn't allow for any small degree vertices. Every vertex has to have degree, excuse me, to at least n over 2. So after Dirac's theorem, people started looking for theorems that would be sufficient conditions for a graph to be Hamiltonian that did allow some small degree vertices. And probably the best known one, and the one that I've used just recently actually, and it sort of gets buried sometimes in books, but Poja, about 10 years later, showed the following theorem, and how you should think of this, excuse me, is that Poja's theorem allows some vertices of small degree, but not too many. So what do I mean by that? He said, if you look at i's between 1 and n minus 1 over 2, so these are what you should think of as small degree. They're the kind of numbers that Dirac doesn't allow. And if whenever you have a small number like this, a small degree, if the number of vertices of degree at most I, so the number of vertices with degree less than or equal to I is less than I, then G is Hamiltonian. Okay, so the number of vertices of degree less than or equal to 1 has to be less than 1 or 0. The number of vertices of degree less than or equal to 2 has to be at most 1. Less than or equal to 3, at most 2, and so forth. So let's look at an example. So here's a graph with 11 vertices. And so to satisfy Dirac's theorem, we have to have at most, everything would have to have degree 5. And at least 5. And they don't. No, excuse me, n over 2 would be 6. So certainly not every vertex has degree 6 here. So this graph does not satisfy Dirac because it has these vertices less than n over 2 of degree. But look at the degrees, and I claim this satisfies Poja. So Poja says it's Hamiltonian. How many vertices of degree 1? 0. How many vertices of degree less than or equal to 2? 1. How many vertices of degree less than or equal to 3? 2. How many vertices of degree less than or equal to 4? 3. Okay, so you can march through and you check that the vertices of degree at most I is strictly less than I. So Poja would say this graph is Hamiltonian. Okay, so it allows some small degree vertices. This is essentially, I'm sorry, I've got some problems like this morning. Too early. Let me take a drink of water. Okay. All right, so this is the way I believe that Poja described his theorem, but I want to look at it slightly differently. I want to do it in terms of degree sequences or sequences that are forcibly Hamiltonian. So how would I rewrite this to give me a forcibly Hamiltonian type result? I would have to start out with a graphical end sequence. So I've got pi that is graphical. So we're assuming it's graphical because Poja starts out if G is a graph with these degrees. And how would we write this in terms of the degrees? Well, I claim it's the following. For the small i's, the ones less than n over 2, d sub I has to be greater than or equal to I plus 1. Like d sub 1 was greater than or equal to 2, d sub 2 was greater than or equal to 3, etc. And I claim this is equivalent. And why is that? Just real quickly, if d sub I is greater than or equal to I plus 1, that means that the ith degree is at least I plus 1. Then how many vertices can have degree less than or equal to I? Well, only the degrees before. That would be D1 or D2 up to Di minus 1. So this is exactly equivalent to this. Now, Poja didn't write it this way, but my next theorem that I want to give you is written this way. Okay. So the next theorem I want to talk about is that of Chvatal. And I know I don't pronounce that right. So anybody who thinks they mispronounce that name right, we're together. But he developed an even better theorem than Poja. And as I talk about these theorems, each one implies the previous one. So they're all getting better in some sense. He actually allowed even more small degree vertices. And he did it in such a way that by balancing how many small degree vertices you have by enough big degree vertices. And this is Chvatal's theorem, which when I first saw it many years ago, I thought it looked very complicated, but now it's kind of a standard sort of result. So he said, if you have a graphical sequence where if it happens for these small i's that some d sub I is less than or equal to I, see, Poja doesn't allow that. D sub I has to be greater than or equal to I plus 1. But Chvatal said, if by any chance this ever happens, as long as d sub n minus I is greater than or equal to n minus I, then it's the sequence is forcibly Hamiltonian. So again, if you ever have this, you have to have this. And if that always happens, then the sequence is forcibly Hamiltonian. And what this really says is, if for some small I, remember Poja said you had to have less than I vertices of that degree at most I, but Chvatal says if you ever have too many to satisfy Poja, as long as you have a lot of big degree vertices, the sequence is still forcibly Hamiltonian. So to say that d sub n minus I is greater than or equal to n minus I, remember all of these things are in increasing order. So if d sub n minus I is this big, then so are all the bigger d's. Okay, so that's why you get at least this many vertices of degree at least n minus I. Okay, and in a really strong sense, Chvatal showed that his condition is best possible for forcibly Hamiltonian, or if you want to think of it as a degree condition. And if you haven't seen these results before, I do want to show you why his is so strong. If you have two sequences of numbers in non-decreasing order, we're going to say that the q's majorize the p's, or that the p's are majorized by the q's if term by term the q's are greater than or equal to the p's. Okay, so the q's majorize the p's. The q's are bigger term by term than or greater than or equal to. And Chvatal's theorem about his result being best possible was that if you have a graph whose degree sequence fails Chvatal, it may or may not be Hamiltonian, that's not really important, but if it fails Chvatal, then that pi, that degree sequence, is majorized by the degree sequence of a non-Hamiltonian graph. So there is a non-Hamiltonian graph whose degrees term by term are greater than or equal to your original graph. So in some sense, if you say that a graph doesn't fail Chvatal, you know, there are bigger sequences that are non-Hamiltonian, so you couldn't fix Chvatal any term by term. And by the way, this kind of condition, this majorization condition, never was satisfied by previous Hamiltonian sufficient conditions. Now I'm going to show you the graph that Chvatal built. So because we're going to be looking at this condition a lot of times. So suppose a degree sequence fails Chvatal condition, or in another way of saying that, suppose a condition or a sequence you start with fails Chvatal's condition. That means that there's some I where both d sub I is less than or equal to I, and d sub n minus I is less than or equal to n minus I minus 1. Because Chvatal said, if you have to have whenever this happens, then this number is greater than or equal to n minus I. So suppose a sequence fails Chvatal's condition. Then here's the graph I want to look at. What I want to show you after I show you two slides is two things. That number one, this graph is non-Hamiltonian. And number two, degree by degree, this graph or the sequence of this graph is greater than or equal to the sequence that failed Chvátal's condition. So, you know, the way you think of this is if you fail Chvátal, then there are graphs that even have bigger degrees that are not Hamiltonian. So you can't bring those Chvátal's numbers down any. So what is this graph? This is a complete graph with I vertices. That's the side that Chvátal failed, or the graph failed. And so this means we have I vertices and all the edges in here. Down here we have I vertices and no edges. That's what this complement means. And these are all the rest of the vertices, and this is also complete. So I have n vertices all together. And I put all the edges here and all the edges here. Now I claim this graph is not Hamiltonian, and in a very informal way. The reason is I have I vertices here, and if you just look at the bottom part, these are all independent. There's no edges, so there's like I pieces here, and this is one big piece. But all together, there are I plus 1 pieces that have no interaction. So to pick up these I plus 1 pieces, we always have to go through a vertex up here, and there are only I of them. So you can't build a Hamiltonian cycle. On the other hand, and I'm kind of talking slowly here, I don't want to spend too much time, but if you look at the degree sequence here, these vertices each are only adjacent up here. So every vertex here is degree I. That's these first I entries, and each one of them is I. These vertices are adjacent to everything in here. So inside here, each vertex has degree n minus 2i minus 1 itself, and then is adjacent to I more vertices up here. So we get what? N minus 2i minus 1 plus I, and that's these entries. And if you count, right here, we're at d sub n minus I. And then these guys are adjacent to everything. So they have degrees n minus 1. In particular, the most important part is this is the ith degree, and it's I. And this is the n minus ith degree. So it's n minus I minus 1. And in here, these are just as big as they could be. If this is I, then these can't be any bigger. And if this is n minus I minus 1, these can't be any bigger. And these are just as big as they could possibly be. So this is homework. Think about this. That says that the graph we started with, who failed Chvátal, is term by term, the degrees are majorized by the degree sequence of this non-Hamiltonian graph. So the degrees of any graph that fails Chvátal are, that degree sequence is majorized by the degree sequence of a non-Hamiltonian graph. Okay, so what you're supposed to think now is, wow, Chvátal is just as good as it can get. So that's one thing I want you to think about. On the other hand, not every forcibly Hamiltonian end sequence satisfies Chvátal. Okay, so there are sequences of numbers that are forcibly Hamiltonian, i.e., if any graph has that degree sequence, it has to be Hamiltonian, but it doesn't satisfy Chvátal's condition. And if, I don't know if this is in our book or not, but it should be. Nash-Williams showed a long time ago, Nash-Williams, I believe, was Chvátal's advisor, that for n that are satisfy some simple parity conditions, that the graphical n sequence that's n minus 1 over 2 everywhere is forcibly Hamiltonian. So first of all, this is forcibly Hamiltonian. That was the work he had to do. And it doesn't satisfy Chvátal. Why? Because if you let I be the biggest possible value that you needed, d sub n minus 1 over 2 is supposed to be, well, anyways, I'm going to let you think about it. You have that d sub I is less than or equal to I, and d sub n minus I is less than or equal to n minus I minus 1. That's what I want to try to say when I is n minus 1 over 2. we'll see a more general one that makes that a little clearer. Okay, so here is an example to show that even though I said Chvátal is about as good as you can get, there are sequences that are forcibly Hamiltonian, but yet don't satisfy Chvátal. So are there a lot of these? I mean, one time when I was first starting to talk about stuff like this, that was a question that came from the audience. Are there many sequences? This one is really special because it doesn't even satisfy Dirac, of course, but the reason it's forcibly Hamiltonian is particularly determined because it's regular. Every single vertex has the same degree. You use the proof of this result to show that that's forcibly Hamiltonian really depends on the regularity of the sequence. So are there others? Well, it turns out that Nash-Williams himself gave a bunch of examples, but let's remind ourselves again before I go to the next slide to say that a sequence pi fails Chvátal. That's true if and only if we have some small I, and you're going to have to remember this, such that both d sub I is less than or equal to I and d sub n minus I is less than or equal to n minus I minus 1. Okay, that's what failing Chvátal means, and I'm going to look at this several times. So Nash-Williams actually, oops, that's covering part of the theorem. I can't do anything about that. Nash-Williams actually proved a stronger result than what I said. He showed that, again, with some parity arguments, if for all these small values of I, if you look at the sequence where the first I values are I, so it's I, and then the rest are n minus I minus 1, that's forcibly Hamiltonian. Now that's not a regular sequence, but it's called biregular. There are only 2 degrees, and that's used a lot to prove this theorem. So first of all, this is forcibly Hamiltonian. That's what he proved. And it fails Chvátal, and this is something that I want to talk about a lot because d sub I is I. So whenever d sub I is I to satisfy Chvátal, d sub n minus I has to be at least n minus I, and this one's n minus I minus 1. So Nash-Williams a long time ago gave this family of sequences, graphical sequences, that were forcibly Hamiltonian and failed Chvátal. And right now we're looking at, are there lots of those or few of those or whatever? And by the way, if you put I equal n minus 1 over 2, that gives you the result I mentioned a minute ago. So far I've been talking about a lot of old results, but something new that we looked at recently was, can we improve this result? And with Doug Bauer and Ed Schmeichel, we did the following. We showed that if you have integers n and I, where we're in exactly the same place we've always been through this talk, that is that I is, you should think of those as I is the degrees of small degree vertices. If we have the following happen, then we know that it's forcibly Hamiltonian. What is the following? If we have all the first vertices, or the first degrees are I, just like up in Nash-Williams. But remember, Nash-Williams said the first ones have to be I, and then the rest are the same. So we have this biregularity. And again, it was forcibly Hamiltonian and failed Chvátal. So how might we improve this? Well, here's how we did it. We left the first I degrees equal to I, just like up here. But then we proved that the following works. If the next so many degrees are n minus I minus 1, and why that? Because we want to fail Chvátal. But then beyond that, you're absolutely free That is, as long as the sequence is graphical, you can put anything you want in here and you will get forcibly Hamiltonian, except for one exception. And that is the one where these are all I, the rest are all n minus I minus 1, except the last one is n minus 1. That sequence is not forcibly Hamiltonian, because I'll show you the example that shows that it's not. My question I want to make sure, and I know we're not having interaction here, but that everybody understands why why we looked at this, because we wanted to come up with some forcibly Hamiltonian sequences that failed Chvátal. We are trying, the big picture is, how good is Chvátal? On one hand, he showed that we've got this majorization thing that says in a certain way you can't improve it, but we're trying to show there are a lot of sequences that are forcibly Hamiltonian that don't satisfy Chvátal. Okay, and here is a family of those. So I just want to show you why these don't count. This one we have to put aside, because here is a graph that satisfies that last, or has that last degree sequence. And we've seen this kind of graph a moment ago. This is just a vertex. This is a complete graph. This is a complete graph. And if you pull off this vertex, you leave two pieces. So it can't be Hamiltonian. And it has that degree sequence that I showed you. Okay, so again, what we're showing is that anything that satisfies that condition that I just gave you, that is any sequence that's I at the beginning for the right number of entries, then n minus I minus 1, and then anything you want at the end, as long as it's graphical, is a forcibly Hamiltonian sequence that fails Chvátal for the value of I that's in the theorem. And we're going to call these Nash-Williams NI sequences, because he was the first to look at these kind of things. N is the order of the graph, I is where Chvátal is fails. Okay, so how many of these guys were we able to create? The final result of that paper, which by the way just got accepted in Graphs and Combinatorics, we got by this number. So let's look where these come from. So these are the I's that we look at for Chvátal being not satisfied. We actually had to build, and remember when we start with the sequence, and this is really important, when you start with a sequence, you have to know it's graphical. So you can't just build these sequences that satisfy these conditions. You first of all have to take a sequence that satisfies that, show that it's graphical. So you have to show there are graphs with that sequence, and then you can apply the theorem. So we had to build a lot of graphs here that satisfied the degree sequence. Then we added these numbers up. We counted them for all the I's, for each I, or I should say, I counted them for each I, add them up. This is just arithmetic. And here we use something called Stirling's formula that bounds binomial coefficients. And what does this notation mean? This big omega means that there's some absolute constant, like a 7 or a 25 or whatever, a C, such that when you add this, when you look at this term, this gives you a greater than or equal to that constant times 2 to the n over root n. The constant's not so important when n is big, but what we proved was something we were surprised, actually, that there are, for any n, there are this many, exponentially many Hamiltonian, or excuse me, graphical sequences that fail Chvátal that are forcibly Hamiltonian. That's, you know, it's exponential. So now I'm giving you data that kind of shows why Chvátal isn't as good as one might think. So, and that's what this talk's sort of about. And so what we want to do now is compare these two things that seem to be opposite of one another. On one hand, Chvátal is supposed to be so good, but on the other hand, I just showed you why maybe it isn't. So let's let C sub n be the number of graphical n sequences that satisfy Chvátal, C sub n, and let S sub n be the number of forcibly Hamiltonian n sequences that don't satisfy it. So I'm just staying in the world of forcibly Hamiltonian sequences. And I want to say, I want to look at what proportion satisfies Chvátal. So here's a picture. This is how you should think. So in the middle are, these are all the forcibly Hamiltonian sequences. So I'm only staying in that world. And here are the ones that satisfy Chvátal. And don't let the picture fool you. The size means nothing. So here are the ones that satisfy Chvátal. And then there's some that don't. And what we want to look at is this ratio. So this ratio is the number of forcibly Hamiltonian sequences, which is this, Cn plus Sn. And we want to say what proportion satisfies Chvátal. Is it big? Is it small? Do we not know? Okay, because we've seen one argument that Chvátal can't be improved much, and another argument that says there are a lot of forcibly Hamiltonian sequences that don't satisfy Chvátal. Right? So these are supposed to be the pictures in your mind. In this picture, the ones that don't satisfy Chvátal are supposed to look small with respect to the others. This picture might suggest that the ratio of Chvátal sequences over all forcibly Hamiltonian sequences might go to 1. And that is, you know, the difference, or not the difference, excuse me, that's the wrong word. The ones that do not satisfy Chvátal are so small with respect to all of them that that ratio goes to 1. That would be Chvátal as best possible sort of picture. On the other hand, maybe the Chvátal condition the sequences that satisfy Chvátal are really not so big compared to S sub n. Even though we had this majorization thing going on, we know that there are exponentially many things floating around out here. So maybe this ratio of the sequences that satisfy Chvátal over all forcibly Hamiltonian sequences goes to 0. And this picture says maybe it goes to something in between, some other constant, maybe only half the forcibly Hamiltonian sequences satisfy Chvátal. Well, we don't know the answer. I have to fess up right off the bat, but I'll tell you what we do know. With a grad student of Doug Bauer's, actually before I got involved, he developed an algorithm. I mean, he generated graphs with various degree sequences. And for, I know these are small n, but it gets very computationally hard for big N. He counted a number, capital Sn. Now, capital Sn is something that we know for sure is greater than or equal to little sn. So that's all you got to remember right now. And then we looked at the behavior of little c and capital S. And he actually counted the numbers of sequences that satisfy Chvátal up to n equals 13. And, you know, these numbers are getting huge. And he calculated this number, which you should think of as an upper bound for little sn. These are the kind of bad sequences, those that are forcibly Hamiltonian but do not satisfy Chvátal. And this number is much smaller. And if you look at this ratio, you might guess it's going to 0. You might guess whatever you'd like, but we were interested in this because it looked like the percentage or the ratio of graphical sequences that do not satisfy, or forcibly Hamiltonian sequences that do not satisfy Chvátal over those that satisfy Chvátal is going to 0. Another thing we looked at with these numbers, this data, is the ratio of the S's as you went to each progressive S, except for this value, seemed to be under 4. And that is all I want to use right now. Or maybe it's going to some constant under 4. So it appears that it's bounded by something under 4. And so if this ratio is bounded by something under 4, S sub n is going to be less than b to the n for some b less than 4. Okay, now I've been throwing out a lot of exponential numbers, and I just want to point one thing out, and that is, you know, if you look at the whole world of graphical sequences, the best known bounds that I'm aware of, this GN, is that's how many graphical sequences are there that are in this form. it's somewhere between roughly 4 to the n over n and 4 to the n over log n root n. So the number of graphical sequences are in this exponential world. Okay, now I want to put this all together and make a conjecture. We have found a lower bound for C sub n, and C sub n is how many graphical sequences satisfy Chvátal. We have found that we can bound, we have a C such that C sub n is greater than 4 to the n over n cubed. And in fact, with one step that we believe, we think we can show that it's greater than 4 to the n over n to the 3 halves. Okay, so let's put this all together. Our data leads us to believe that S sub n, those are the sequence, well, that's an upper bound for the sequences that are forcibly Hamiltonian, but do not satisfy Chvátal. And we've said that we can prove this, a lower bound on C sub n. So if you put this all together, this ratio that we want to look at, what proportion of forcibly Hamiltonian sequences satisfy Chvátal, and you do some arithmetic, you can rewrite this way and you get this inequality, and I'm just going to skip through some of the arithmetic here, but you end up with this ratio, at least for n up to 13, is greater than 1 minus epsilon to the n for some epsilon less than 1. And what does that say? Well, this goes to 0, right, as n gets big. And consequently, a conjecture that we made a couple of years ago is that even though I gave you 2 arguments about how good Chvátal is, we believe, one argument said it was very good, one argument said maybe not so good. We believe that, in fact, that ratio of forcibly Hamiltonian sequences that do satisfy Chvátal goes to 1 exponentially fast. So this is really the main conjecture. And if this is true, that's why we said essentially Chvátal is not only sufficient, but necessary, because a sequence goes, the number of them or the ratio goes to 1 exponentially fast. Okay, so that's part 1. Oh my goodness, we better hurry along. So now I want to just mention k-connected, because I want to show you another property, and I want to look at exactly the same kind of questions. Here's a property. Here is a best possible type result that looks very much like Chvátal's theorem. Then I want to say what proportion of forcibly k-connected sequences satisfies it's a Bondy result. And then I'm going to argue that one doesn't go to 1. So we have a very different behavior of these forcibly k-connected sequences. All right, so k-connected means you have to remove at least k vertices from a connected graph to disconnect it. Okay, so you start connected, you want to remove some vertices until the graph falls apart. And k34, which we've seen before, if I remove these 3 vertices, it falls apart. And I'm going to claim that no matter how you remove 3 vertices, or excuse me, 2 vertices, it does not fall apart. So this graph is not, it is 2 connected, but not 3 connected. Oh, excuse me, it is 3 connected. I misspoke, because you have to remove at least 3 vertices to disconnect it. So it's highly connected. Well, back in 72, which was essentially the same time as, I think Chvátal and Bondy went to school together. I think they were in grad school together at Waterloo. He showed a very similar sufficient condition for a graph to be k-connected that looked a lot like the Chvátal result. You're given a k, you want to give a sufficient condition for a graph to be k-connected. And he showed that for, again, think of these as the small i's. If d sub I, whenever d sub I is too small, now this one was different. It wasn't d sub n and an I and something else, but the result did contain I. If d sub I is too small, then some bigger d has to be greater than or equal to n minus I, then the graph is forcibly k-connected. Okay, so it's a similar type result. Too many if whenever there are too many vertices, a small degree, you have enough big vertices, the graph is k-connected. And he showed that this was best possible in the same sense as Chvatal. That is, if you started, well, let's maybe put the whole thing. If you have a graphical end sequence that fails Bondy's condition for some I, then I can build a graph. And let's just look at this. I claim this graph is not k-connected because I can pull out these k-1 vertices and I end up with two pieces. So it is not k-connected. You don't have to remove k vertices to disconnect it. And if you build or look at the degree sequence of this graph, and you take any sequence that failed Bondy's condition, then that sequence, the one that fails, is majorized by this one, that is the degree sequence of a non-k-connected graph. So far, this picture looks just like Chvatal. You know, I have a theorem and it's best possible by this majorization thing. However, we believe, and we almost can prove this if we can prove it if we use a very famous conjecture, that in this case, we don't get the same sort of proportional results. That is, we can show using a very famous conjecture that we'll mention in a moment, that the proportion of forcibly k-connected end sequences that satisfy Bondy does not approach 1. And the sequence or the conjecture that we need to use is a conjecture by Royal about this number G sub n that we bumped into a moment ago. That's the number of just graphical sequences. And Royal conjectured that the ratio, as you go along from gn minus 1 to gn, goes to 4. And this is pretty well accepted by people that work in degree sequences, which says that any gn, the number of graphical end sequences, is approximately, there's some constant in there, 4 to the j times g to the n minus j. And remember, our world of graphical sequences is sitting here, so that makes some sense. And if we assume Royal's condition, we can prove. So we can prove using Royal's condition that if you look at the proportion of forcibly k-connected end sequences that satisfy Bondy's condition, so this is just like the ratio we looked at for Chvátal, that ratio is bounded above by this number. It's not a good bound, but it is bound by this. But what's surprising about this number, there's no n in it. So as n goes to infinity, this number, this bound stays the same, and this number is less than 1. So assuming Royal's condition, you do not get this proportion going to 1, even though the conditions look very, very similar. So in sort of conclusion, we can say, we'll call a graphical property increasing if whenever you have that property, adding edges doesn't destroy it. Like Hamiltonicity. If a graph is Hamiltonian and you add an edge, you can't destroy that it's Hamiltonian. So that's a increasing function or property. And a property is decreasing if you take away an edge, doesn't take away the property. So like if you know what k-colorable means, if a graph is k-colorable, taking an edge doesn't destroy that property. And in a paper, I don't remember, 2015 with lots and lots of authors, they showed that every such property, this is called, if it's monotone, it means it's either increasing or it's decreasing. And every such property, every monotone property, had a best monotone degree condition that is analogous to those we've seen for Hamiltonicity or k-connectedness. That is, if you have a monotone property, you'll have a degree condition that is best possible in this majorization sense. Okay, that's what I mean, analogous by best possible. So we've looked at how many forcibly Hamiltonian sequences satisfy Chvátal. We've looked at how many forcibly k-connected sequences satisfy Bondy. For any monotone property, we could look at how many graphical sequences satisfy that monotone condition and look at that ratio. So again, well, this is what I just said. In part one, we can conjecture that if P is the monotone property of Hamiltonicity, that ratio goes to 1. And we would love to be able to prove that. We're working on it. Part two, we conjectured if P is k-connected, then in fact, that ratio is always less than some constant that's less than 1. So it's not going to go to 1. And of course, other properties, we don't know what happens to that ratio. So this is my big category of problems that I'm giving to you. Anytime you have a monotone property, and there are gobs of properties like this, and people have written lots of papers about these kinds of conditions, but people have not looked, I don't think, at this ratio. And finally, then, some open problems for us in particular. If you have an answer, please let me know afterwards. As a first step to proving this goes to 1, okay, this is going to be something I have to admit, embarrassingly, we don't even know a constant, and we can say this ratio is greater than or equal to that constant. You know, we can bound, we have a lower bound on C sub n. It's at least 4 to the n over n to the 3 halves. We have a lower bound on S sub n. What we don't have is an upper bound. And that's, of course, what the next question is. And finally, of course, what's the complexity of C sub n? That would be an upper and lower bound. You know, a C sub n roughly 4 to the n. For those of you that do Hamiltonian stuff, you can prove in the probabilistic sense that almost all graphs are Hamiltonian. That is, you know, the ratio goes to 1. It's not true that almost all sequences are Hamiltonian or, you know, forcibly Hamiltonian, but we think if you stay in the world of forcibly Hamiltonian, then the ratio of Chvátal to those goes to 1. And I think I finished right on time. Thank you very much.
Okay.
Thank you very much, Professor Linda, for your very interesting talk. So we will continue to the Q&A session, but before that, Professor Baskoro has something for you.
Thank you.
Okay. Okay. So I would like to present some performance. This is a song.
Excuse me, can my
Yes.
husband come in and hear this?
Sure, sure.
Yes, of
Sure.
course.
Yeah, sure. Yeah. So let me share our
And my dog.
screen. Yeah. This moment.
Performance.
Okay, just let me. Oh,
This is a performance.
oh.
This is something
Okay.
that's a performance.
Can you let me see. Here we are. So yeah. This moment. Okay, full screen. Yeah. So this song sung by one of our colleagues and the group, which is Rinovia Simanjuntak. She's here actually. And now let's have a look.
Once in every life, someone comes along, and you came to me. It was almost like a song. You were in my arms, right where you belong, and we were so in love. It was almost like a song. January had to
Okay, so I hope you enjoy.
It was lovely, lovely.
Okay, Reno, can
Yes,
you? Here the singer.
I'm not singing.
Reno,
No,
yeah. One
Hi,
of
Linda. How are you?
I'm fine. I'm fine. Thank you. That was beautiful. Beautiful.
Thank you.
I don't think I've ever been sung to after a talk.
Okay, back to Prita.
Okay, okay, so we will continue to the Q&A session. So if you have any questions to Professor Linda, you can ask directly to Professor Linda. So, there any questions from the audience? You can raise your hand first, or you can just directly open your mic and ask the questions.
It's probably late on Friday. So,
No worries. Okay, Professor Stanislaus, you can ask
Hello.
directly to
Hello,
Professor Linda.
thanks for great talk and
oh wait,
refreshing.
who is speaking? Who is speaking? Oh, Stan. Okay.
Yes, thanks for great talk
Stanislav.
and refreshing my memory on some old, beautiful classical problems.
Yeah.
But my comment is, you know, even with those very hard old things, one can go forward. So that's wonderful that you can add little as it is, but we can go forward. So maybe that's a message to the
Yeah.
those
I
start-
wanted, right. Do you have a question? I'm sorry, I interrupted. Go ahead.
No, go ahead.
Oh, well, I was just going to say that with a group that I worked with a couple years ago, we actually had to pull Poja's theorem sort of out of the dusty books. And a lot of books don't even mention Poja anymore because Chvátal's better, etc. But it's hard to use. So, you know, when we started trying to prove something, and we actually proved some very, very nice results, we were looking at edge conditions and k-partite graphs for Hamiltonicity. And we used Poja over and over and over, and Chvátal would have been too hard to use. So, and most people didn't know that result. So sometimes, you know, going back to some of the old results get you things that you wouldn't have had before. So that's one thing. And just sort of a humorous story, when I was looking for examples of graphs that were sequences that were forcibly Hamiltonian, but not Chvátal, when I finally found that theorem of Nash-Williams, no one knew where it appeared. And in fact, it doesn't seem to have appeared anywhere. And I contacted, well, Nash-Williams is gone, but I asked Chvátal, and he said, oh, I know where it was laying on my shelf. It was a university report. It was on my shelf, but I have no idea where it is. Bondy said the same thing. I don't remember who else I asked. I finally found a paper that said exactly that. It doesn't appear to have ever appeared in, you know, in a journal. Even Nash-Williams referred to things that didn't have a proof. So people there was no proof even of the Nash-Williams sequences. So, you know, some of this stuff, pulling it up again, you find interesting history to it. So anyway.
I have one question. Maybe, you know, recently I'm looking more at complexity theory. So yes, under the hood, the Hamiltonicity is incomplete. Do you think any chance of complexity classification of these forcibly sequences, Hamiltonian
I don't know.
sequences, is
Well, that's
feasible?
one of the, yeah. You mean how many sequences are forcibly Hamiltonian?
No,
Not
how
Chvátal?
difficult it is to decide for a sequence.
Oh, it's
whether it is
probably
or not.
just as difficult as the Hamiltonian problem, I would think. Yeah. Yeah.
So that,
So
that
it's
can
not-
be hard.
But you know, what we're looking at is bounds, and that's why we were looking at it, you know, probabilistically. So maybe that's what you were asking, but you know, counting, can we get bounds on these forcibly Hamiltonian sequences that are not Chvátal? Can we get bounds on the ones that are? And you know, now we're trying to get, we have a lot of ideas about bounding that S sub n, the non-Chvátal forcibly Hamiltonian sequences, and that's where we're working right now. So, I mean, it you know, just by constructing those and somehow bounding them, it's real hard to work with Chvátal. Well, I mean, because you've got those two conditions, but
Thank
we
you
hope
very
we'll get somewhere. It's been fun. Thank you. And as I said, I'm going to be near Yazwo next week, which is where my grandpa was born. And I hope to meet some family that I didn't even know existed. So it's going to be quite an adventure. But first, I'm going to a conference in Gdansk for women in mathematics. So we have a
I'm
big trip
jealous.
planned.
I'm jealous. I would go myself.
Yeah.
Both
I've
north and
been to
south.
Poland many times, but I did not know I had family. I mean, I assumed I might, but I didn't know precisely where this family was. Yeah, thank you. I hope we meet again soon. Are there any other questions? Because I have one thing I want to say. Oh, thank you.
It's okay, Professor Linda, you can go.
I can talk now, right? Some more.
Go ahead.
You know, as you notice, you know, I actually began my career in 1974, quite a long time ago. And when I began my career, there were literally no other women. Fan Chung and I were almost always the only two women at conferences. So early on in my career, I did not worry about women in mathematics because I was one of the half or something. I mean, there weren't organizations, and it was not easy. And then I was having to write papers and things, so I didn't have time to be real involved in those issues. But in the world of mathematics, and graph theory in particular, it still is a struggle for women because if you look at data, women are not getting to full professorships. And in fact, next week in Poland, I'm on a panel to talk about that. So about 3 years ago, someone approached me and said, you know, maybe we should put together something like number theory has done, that is a women in graph theory. There is a women in number theory. So we did, in fact, apply and got a big NSF grant. And we ran a program for a week for about 50 women. It was 6 teams, and each team was working on a research project. And as far as I know, they're all still working. Everyone published something. I had a team. My team's still working. So it truly was successful in that way. But at the same time, in kind of from a different point of view, we started something called Women in Combinatorics. So it's more broad. We didn't have a conference, but it started out sort of with the notion that we would have a database of women in combinatorics all over the world. I mean, I think we have 300 people now, and men too. They can be on it, or at least access it. And the beginning was to have a database where there would be women who would be interested in speaking, or if you need a roommate for a conference or whatever. And especially the speaking part, because I have to say frequently I'll have a guy come up to me and say, oh, we'd love to have more women at our conference, but we don't know any. Well, now I can tell them, go to our website. You can find lots. I mean, I hear that a lot. You know, I go to conferences and there are 3 women and 47 men. And I say, well, why are there so few women? And one common answer is, well, I just invite my friends that I work with, which means you'll never include more. And the other is, gosh, we'd love to, but I don't know any. So here you go. Here's a database. But in the 3 years, especially through the pandemic, Women in Combinatorics, also called WinCom, I'd love you to go and look at the website. Just look up Women in Combinatorics. We not only have this enormous database, we have had weekly colloquia for young women who didn't get a chance to go to conferences during the pandemic and show what they're doing. So we had almost weekly, and then it went to bi-weekly colloquia hour-long colloquium and with a little, wine and cheese in your own house on Zoom social hour. We've also started a mentoring program where young faculty can mentor graduate students or postdocs, and senior faculty can mentor young faculty. I never had a woman professor in mathematics. I never had a woman mentor. I was very lucky to have very good male mentors, but it's not the same. Just some people, there's some things you'd really like to talk to somebody who looks like you and has your same problems, right? And the other thing that we've done more recently, this was really cool. Elsevier contacted me and said, would you like $5,000 to do something with your program? So we decided to give some small scholarships to women in math. It turns out it was mostly undergrads in combinatorics to help them. And we gave 4 scholarships to women in Mexico of $500 each. And I've been assured that means a lot to someone there. And we're going to give 6 to women in some African countries, but with the pandemic, we sort of got stalled with being able to organize that. So I'm pretty proud of WinCom. It's not me that did most of it, but the fact, and we're going to have a lunch, I believe, it started with a lunch at a Canada meeting. We just invited all the women that were there if they wanted to come and talk. And we realized there were a lot of women who wanted to come and talk about other things than mathematics, but living in mathematics as a woman. And we're going to do the same thing at Canada this coming year. I don't know if any of you ever get to Canada, but for sure, I wish I had a slide, but just look up women in combinatorics if you're interested, or if you're even just curious to see. We have a student who did a spectacular website for us that has this, and sign up for the database, and you can see the kinds of things we're doing. So, very late in my career, I'm trying to help a little because I don't see the number of women that make it to full professors. The data is something like 10% of full professors are women. Now 30%, at least in the States, of PhDs are women. So what's the problem? And it's no longer that, when I got out, I was told, we're not going to hire you because you're a woman, it's too much trouble. That was absolutely legal. You can't do that now, at least in the US, but what are all the reasons that keep women from dropping out? First of all, they don't, they drop out, or they don't get to the advanced levels, which means they don't get grants, which means they don't get invited. They don't get to do all the things that they don't get paid as much. They don't get to do the things that they ought to get to as senior people in their careers. So I still do a lot of research. I'm actually retired from teaching, but I do a lot of research. I work at Western with grad students. And the third little component of my career now is to try harder to talk to both male and female grad students about what I perceive are some of the problems. I think a lot of it is completely unconscious. I only invite my friends, or, I usually invite my friends to my conference. Well, if your friends are all guys, it means it's never going to get any better, and that kind of thing causes problems. So that's my 2-minute bit on women in combinatorics. And if you have any other mathematical questions, I'd be glad to answer. Okay. And come to Canada if you want to see us in action.
Okay, Professor Linda, actually there is a question from Professor Baskoro.
Okay.
Okay, so Linda, I'm just curious how hard to find the necessary condition for being Hamiltonian.
And be complete.
Is it possible to revise?
Well, there are some necessary, but then they're not sufficient. For example, it has to be too connected. It has to be too tough. It has to, there are necessary conditions.
Okay.
But not sufficient.
Yeah. Oh, I see.
Necessary and sufficient would be, if you could find that, it would be the same as solving the NP complete problem, which a lot of people don't think will ever happen. But
is it possible that if we would like to find necessary and sufficient condition from Chvátal condition or Nash-Williams condition, and to improve this condition to make to be necessary
Closer?
condition.
Yeah, I think that's kind of what we're, yeah,
Oh, we
kind
have
of what
to-
we're doing. We're, you know, when we look at, I think what's happened, Eddie, and I'm not sure I understand exactly your question exactly, but a lot has gone into more of a probabilistic sense, like this ratio we're looking at, you know, so because it seems like it's going to be hard to find that necessary and sufficient condition that catches everything. So that's why we started looking at that ratio, you know, how does Chvátal work versus all forcibly Hamiltonian? So that was our way of looking at it. People have looked at just the ratio of Hamiltonian graphs to all graphs, and that, you know, that goes to 1. So almost all graphs are Hamiltonian. But if I hand you a graph, a big graph, and you have to tell me whether it's Hamiltonian, we don't have any. And I'll tell you, there are so many applications. I saw Bill Cook giving it a phenomenal, really fancy, I mean, he was on a stage and he had a screen that was a whole room size, and talking about everything in the world that Hamiltonian is a problem under, you know, all kinds of stuff with computers and, you know, operating systems and scheduling, and, you know, so this is a huge real problem in the world. So they do a lot of approximation algorithms too. You know, they get most of the vertices or something like that. So I think people believe it's a very hard, you know, that it's not likely you're going to find a theorem that says a graph is Hamiltonian if and only if, like you have for Eulerian, you know, or an efficient algorithm, you know. So it's, there's probabilistic algorithms too. You know, it cranks out and it will say yes or no, and then it says, I can't tell you, you know, and then it just, and you can get a bound on how good is that algorithm, but there's going to be a pile of things you don't know the answer to.
Okay, thank you very much. Yeah.
Yeah.
Back to Prita.
Okay, thank you, Professor Linda and also Professor Eddie. So is there any other questions? You can raise your hands or you can ask directly. Oh, there are no questions. If there is no questions, then let's give applause virtually to Professor Linda.
Okay.
Thank you very much for your nice talk and also for your sharing regarding the women's in combinatorics. So
I hope everyone signs up or at least gets on the website. It's really quite a beautiful website.
You may include combinatorics from Indonesia. We have many women combinatorics here.
And all the men too should look at it.
Yeah, sure.
I think some of us are already in the database.
Fantastic. I have not looked at it. It gets larger and larger. So, but yeah, I would hope so. It started out, I have to admit, we were talking about women in North America, and then immediately we got some Mexican women, and then it went all over the world. So it's wonderful.
In fact, our combinatorial mathematics president now is woman as well.
Yes.
So I heard it. So is the association for, in Mexico, the whole Mexican association is headed by a woman, one of my colleagues.
And also
we're making some progress.
Math Society president as well as many women. Yeah.
Well, maybe you guys are doing a lot better than we are.
Okay.
Okay. I think I will send the chair to Professor Baskoro again.
Okay, so thanks again to Professor Linda Lesniak.
And by the way, I do want to thank the beautiful music. That was gorgeous. Did one of you write that song? Is that
no, but one of us arranged the song. I think it used to be a pop, a country song actually, from the 70s.
Really?
Yeah.
Well, it was clearly a love song. It could easily be a country song, I guess.
Yeah.
And thank you so much for being in touch and singing with me. Okay, or to me.
You're welcome.
You can invite her to come to your conference. And then to sing the song.
Oh, that's even better.
Yeah.
As soon as I have airfare for you.
Okay, so on behalf of the Combinatorial Mathematics Research Group and the Faculty of Mathematics and Natural Sciences, we would like to present you a certificate, Professor Linda Lesniak, and also some token for the appreciation. So let me show you the certificates. Okay. So this is this is the certificate of being a keynote speaker in our program, and
It's
now
beautiful.
this-
Thank you.
And this is our token of appreciation to you.
Thank you very much.
So I
Thank
will
you very
send these two documents to you probably tonight or tomorrow. Yeah. And again, thank you very much for being in this program.
And please, anyone who has any questions that you think of later, if you want to contact me, I don't remember if I put my email on my talk,
Sure.
but certainly if you have it.
And we like to ask you also your slide, your beautiful slide.
Sure.
Yeah.
You want me to send them? I'll send them right now because
Yes,
I'm off to Poland in a day.
Yeah. Okay, so bye-bye from now, and thank you for everyone. Thank you, Professor Rasisowski, for being tonight and this morning there, and also to everyone. Okay, so bye-bye.
Thank you.
And
Thank
see
you.
you next 2 weeks. Yeah. Okay.
Bye.
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 Bye-bye. Bye-bye.
Bye-bye.
Thank you.
Dilakukan oleh kepala